to everybody. Thank you, Kuldeep sir. So I welcome you again, all the participants in the second session of the third day, this 1 week long FDP. And in the last two sessions that was with me, we have seen the introduction, background, the history of the AI machine learning. And in the last class, that was most important class, I think so, for the beginner. And we have seen very basic terminologies, very important concept about the AI machine learning. And later, I have demonstrated with the coding how to split the data set in the different segment as per your choice. That was the brief about the content we have covered in the previous classes. So today I have taken now I think it is a right time to give you a whole holistic idea how to take the problem, the data set, how to pre-process it, how to uh, choose the any machine learning algorithms that fit on the given problem, and whole the software or the model development life cycle we have seen in the last class. It's time to go through from beginning to the end. So the problem I have taken for the discussion today is the predicting medical expenses. So what is the exact problem and how we are going to solve it throughout the time I will cover. And the underlying machine learning algorithms that is selected for solving this problem is the linear regression. There is a reason why the linear regression only I have selected. There are two reasons. First reason is that you guy, I hope most of the guy are from the mathematics background, and they may have a very brief understanding about the linear regression, what it is. And if some of the participants don't have that background, don't worry at all. The algorithm itself is one of the simplest machine learning algorithm, but most powerful. Don't underestimate that it's simple. That means it is not powerful. It's widely used in variety of areas. So these are the description and brief about the title I have selected for today's discussion, and the content I'm going to cover is like that. So okay, the focus is that the problem I have taken about the prediction problem, because most of the supervised learning so comes under the predictive data analytics. So I'm not going to discuss those words like what is the predictive data analytics, what is the descriptive data analytics, what is the prescriptive data analytics. That is a different segment. So regression is a kind of supervised learning, and supervised learning comes under the predictive data analytics, where we always try to predict something. So here the objective is that to going to use the linear regression for solving the medical expenses prediction. So a human being or for a particular person or for a particular family, the next year how much he or she is going to be spent for the health related issue, that is a problem. And basic contents are there. The R installation, data import, and data expression already covered in the last class. I'm not going to repeat it. I will introduce the basic fundamental concept of the linear regression, because the linear regression is very exhaustive the topic, and many things are there. So it's not possible to cover in the one go. So basic essential part I will cover. The prerequisite is the most important part. Purposefully, I have included over there because most of the time the participants start learning machine learning algorithms and they don't focus on, or they overlook the prerequisite. Prerequisite is why it's so important, because there is no any machine learning algorithm that is versatile and that the algorithm that you can is perfect algorithm. It is not like that. Whatever the algorithm you know or you will study in the future will work on some assumptions. If such kind of assumptions is fulfilled by your data set or environment or setting, then algorithm will perform better. Otherwise, algorithm is going to fail, whatever the algorithm it is. So the assumption, or sometimes called prerequisite, before applying, before selecting algorithm is most important part. And that's, I promise, the implementation I will going to demonstrate with you throughout the R coding and model optimization also. So that is a software model development life cycle, and throughout the beginning to the end, I will follow it. So that is also the part and understanding we have already discussed in the last classes. So I'm not going to repeat it. The background, like someone have requested, what is the background of the problem I have taken? Like everybody, most of the person already experience have purchased the health policies. So when you go for to purchase the health policy, there are variety of different companies are there based on your age, based on your dependent and family income or history. They offer the premium. So the problem is for the companies, how can they decide the premium? So in the one line, the problem statement is that how the health insurance related companies can mm, find out a very suitable or ideal value of the premium. The reason is why. Suppose the premium is too much low. So in that case, the company is going to sell a lot of policies. But in the real life, in the coming days, when the claims will come, uh, the company will going to lose the business. And because company didn't earn a lot of corpus in the form of premium, premium was low, but during the claims, the company has to pay a lot. Opposite also may true. Company, if the company keep the premium of the policy is too much high, nobody is going to purchase it. Again, it is going to lose the business. So the question is that how to accurately we can calculate the premium of the policies. So here the people started working on the applicability of the AI or machine learning, whether they can be helpful to give you a better sense, a better extra hand to decide the premium or the suitable premium. So because the premium of a particular policy is depend on variety of parameters, variety of features. It may be included the age of the person, number of dependent, the person is a smoker or not, health status of the current health status of the person, the family members, age of the family members, history, which part of the country that person belongs, many their routine life, and many things are there. And what kind of hospitals and other facilities around the person stay over there in the city. Many factors are there. So for a human being or for a particular person, it's become a very uh, complex task to consider all those parameter and the impact of parameter they must know. So it's become a, you can say, the non-deterministic problem sometime. So that's why people started working with the solution, maybe with the AI or maybe using any of the underlying techniques. And today we are going to use the linear regression. So that is the background of the problem I have taken. And the data set. So the data set, last class we have seen, this is a data set already available in Google, or if you request, I will share. So data set is with you. For keeping the things very simple, we have considered very limited number of features, because in the real life may have 100 or 200 features. So as you know already, now you have enough knowledge. If you want to predict something, you require a target variable that may be one that in real life you want to predict, and other variables may be a internal variable. So if I ask the questions to you, mm, in the given problem, which one is the target variable or output variable, and which are the input variable? So many of the you may have a uncomfortable stage to answer that question. The question is that, suppose here the data is given about the age of a person, gender, BMI, children means number of dependent, you can say like a 1300 number of dependent, whether person is smoker or not, and which part of the country person belongs to, or expenses. Since machine learning is a area of computer science where it depend on the whole data set. So the data set, we have a historical data set, means we have the data set, you assume that already. The data set says about what? The data set says this person age is 19 year, the female, BMI is 27.9, no children, smoker, yes, southwest part of the country belong, and the last year expenses of that person related to the health issue was like 16,884 rupees, dollar, whatever you want. So this is the way how you can understand the data set. Similarly, a lot of persons are there. Okay. So if my model is able to understand this mapping or can able to predict next year medical related or health related expenses, if I have a such model, then it is very easy for a company to decide the premium of a particular that person, because nowadays premium is not a fix, different person, different family members have a different premium. That's why. So if you apply somewhere in the company, if company is able to find out with the linear regression model, like this is the amount more or less, it's you are going to be suffered in the next year, the company can decide the premium accordingly. So now you can understand through this example, this expenses is going to become a target variable. So if my model is able to predict in the real life, the expenses is very good for me. And other variables like that, these are the input variables like age, gender, BMI, children, smoker, region. Many of you might have a concern about that region of the country, how can be an important parameter for a premium or for a health issues, because we have seen in most of the in a developed country, suppose you are living or belongs to the particular city or particular state, that a lot of minings going on, full of pollutions are there. Like in Delhi, we nowadays talk about people have a lot of lungs related issues. So similarly in Jharkhand or other part of some area I don't remember, having people suffer a lot of skin related issues or cancer related issues. So this way, this part or area of country or city also become important. BMI talk about the your how your weight or age related balance, whether you are overweight or underweight, like kind of things. So these, assume that these are the internal variables, all are important. I'm going to consider these internal variable and we're going to apply the linear regression. So the age, the variable, the data set is given to you, and each and every feature variable I'm explaining in this slide I have already done. Gender, like BMI, children or dependent, smoker is also yes or no, region, so that part I have explained each and every variable of the data set. So here if I say which is the categorical variable with the numerical variable, now you can understand, since age is a numerical variable, BMI is a numerical variable, others all are the categorical variable. Gender, smoker, region are the categorical variable. Or since output variable is a continuous variable, so you are going to predict a number. That's why under the supervised learning, this problem comes under the regression problem. So if it would be if it was the categorical variable, then we cannot apply the linear regression. Then we have to think for the another class, under supervised learning comes under the classification. Since we are going to predict some numerical value, so it comes under the regression problem. Going ahead, so that part I'm not going to repeat. It means how to install, how you can install R and other stuff. Everything I have covered in the last class. What I'm going to do, I'm going to directly going to set the working directory, because my data set is here. So I'm going to copy that path here. I'm going to just open the editor R Studio for you. It will take 1 or 2 seconds. It is ready for you. Yeah, set wd is the command, everybody know. Okay, my data set is in this path. That's why I'm going to set this path as a working directory. I want my programming very easy by doing that way. To rewrite, wait. 1 minute. I need to replace all those things with the backslash. Yeah, so it's successfully I have changed the working directory. Now this is the insurance.csv, already a file I want to import in my R environment. So the code is here. Now you can understand, many of you easily can understand, like read.csv function I have called. Insurance.csv is the dataset name, and string as a factor true, because whatever the string and characters means, like a gender and a smoker and region are there, I want to make them as a factor. Means I am going to tell the algorithm, don't consider it like a string and character, these are the categorical variable. Explicitly I'm going to convert them as a factor or as a categorical variable. So my insurance data set I have uploaded, and by using the str command you can confirm whether the data are in the same format that you are looking. Yes, so these are the integer and it is a factor with label 2, gender, female and male. Similarly, smoker have also 2 factor, yes and no. Region have a 4 labels, north, west, east, south, like kind of things. So I have uploaded my data successfully in the R environment, and I have rechecked it whether it is in a current or desired format what I was looking. So this thing's over. So table command I have demonstrated yesterday. I'm not going to repeat it. I'm going to just starting the brief introduction about the algorithm we are looking today. It's a linear regression. So the linear regression is one of the most well-known and well-understood algorithms, comes under the statistics and machine learning. So if someone will say, sir, answer or explain the linear regression in one line, then it's better to say the linear regression is nothing but a simply equation of the line. So make the discussion very simple. I'm going to call it simple linear regression, not a linear regression. What is called simple linear regression. So it is a line. So you can understand the equation of the line is like y is equal to b0 b1x. Sometimes people are very comfortable to connect it like y is equal to mx plus c or c plus mx, both are same, where sometime it represent in literature like b1 x1 and y. So it is equation of the line where this b0 and b1 everybody know is called coefficient, and x1 is what? Input variable. Input variable. I'm just mixing the mathematical concept of the linear regression, the term of line, plus how way you can associate your data set with that line. So whatever the input variable that comes under the right hand side, y is always the output variable. Or suppose you have a data set having only age, assume that only age and expenses. Suppose there is a 2 variables in your data set. Okay, so y is equal to going to be expenses, and that is b0 plus b1 plus age. So this is the structure you can relate how equation you can populate, you can associate it with the data set you have. Where in term of line equation you say, in typically we know, suppose this is the line. So when the line intercept at the y-axis, it is called b0, or angle with respect to the x-axis we call slope. Slope means b1. Okay, so these are the two things in terms of mathematics you can understand. The line that cut the part of the y-axis is called b0, or b1 is the slope with respect to the x-axis. Okay. Now you may say, if you have more number of variables, so it doesn't make any difference. Output variable, as I explained in the last class, always be 1, expenses, b0, like similarly b1, age, plus b2, gender, plus b3, BMI, like that you can continue. So when you have a single input variable. We have a single input variable we call simple linear regression. And when you have a multiple input variable we call multiple linear regression. So there's a two terminology, a very simple way I have just covered: simple linear regression and multiple linear regression. It is related with the number of input variables. If you have a single input variable, simple linear regression. If you have a multiple input variable, you have a multiple linear regression. There is also polynomial linear regression I will cover. Okay, so don't focus on right now. Why B0 is important? If you ask, then in terms of machine learning, I can answer it, but you need to understand what is the degree of freedom. So please uh, note that word and you try to explore by yourself degree of freedom. It is not right time to cover. So degree of freedom is something I want to it maximize. I want to it maximize. So once whatever the variables are there, every input variable is associated with the coefficient, but we have an extra coefficient that will increase the degree of polynomiality. So that is the one simple answer I have given. It is not itself much clear, but my purpose was to introduce this terminology before you, the degree of freedom. Now, going ahead for a discussion, sometime if you have a multiple linear regression means it is not aligned then. If the data in the three-dimensional or multi-dimensional, so ultimate what you are going to do. So you are not going to draw a line like this. I will not talk about much the line. Then it will become the plane or hyperplane. So the concept is very much simple. So if you have a one input variable, then it is a line, otherwise it is a plane or hyperplane. So now a very important concept again I am going to discuss. Suppose you have a y is equal to b0 plus b1 x1. Suppose this is the equation you have. So most important part are this. Most important part are the coefficient, because you know it is the algorithms. This concept I think everybody understand. It is the algorithms to feed the data. I request Rituraj Dechi ji. Rituraj, I'm just requesting to every participant, please mute your mic. Okay.
I'll be muting him, sir. I'll be muting him.
Sure. So once you feed the data to the algorithms in term of training, you will find y is equal to, like, suppose 5 plus 6 x1, like that. So during the training that I will explain today in the mathematics behind that, so you are going to estimate all those values. It is very important. Why it is important? So suppose same problem is given to the multiple students in my class as a project, and I will say you apply and use your brain to solve that problems. So one student may come with this solution, depend on how the data processing he has done. So the different technique you apply for the different process data processing means ultimate every student will have a different data set, different characteristics of data. Like that means a simple data set I have given, that is a dirty data with noise, a lot of things are there, it is not good for the linear regression. And I have given the enough knowledge to all the students to about the data pre-processing. Based on their understanding, every student it's high chance will apply different data pre-processing techniques and methodology based on their understanding. So ultimate, after applying the techniques, they have a different data set. If they have a different data set, they have a different answers, different linear regression, different model will have automatically. So some student may come like that, sir, my solution is that. Somebody will say, no sir, my solution is like that, like one. So The important point is over there, the magnitude. You need to see the magnitude. The magnitude of the coefficient. So if or student may have comes with another more number of variables like 8x2 like that. So some student may come with a solution having a single variable, some student will have a multiple variables. So you need to consider two things to decide before which model is a good. You have to see the magnitude of the coefficient plus number of coefficient. Two important parameters are there. If you have multiple solutions, these are the multiple solutions. So coefficient, magnitude of a coefficient, always try to small and also try to make it less. So any of the model, I assume that the performance are almost equal. So first parameter, that which of the model give the highest performance, the better performance, it is significantly bigger than others. Try to catch the word. If I say, suppose you have a 3 models, and if y1, y2, y3 have equal accuracy, equal performance, then we have to decide which one is the better. So these are the criteria. The model which have a small or very less, very magnitude is very small, the model will be very good. If the person having a solution having very less number of features, very good, that is a better model. Okay, but if the condition is not good, y1 is much better than other variables or other solutions, y2 and y3. We don't need to go in that way, because this is the methodology and parameter you have to apply when the performance of the set of models are almost equal. You are not able to decide which one is better. So you need to see all those ways. It is directly related to overfitting, underfitting. I am not discussing that part, but try to memorize that word, overfitting or underfitting. So these are the terminology like Amitabh Bachchan in the Hollywood or Bollywood movie in the India. So like if you are from the machine learning, if you don't know overfitting, underfitting means you don't know the Amitabh Bachchan. So, but it is not right time for me to discuss over about the overfitting, underfitting. Just go through the name. You must know. I have listened that name. So these overfitting, underfitting is the most important part of the machine learning. Is directly related to this concept. Okay. So in future, when you will go for the further advanced study, you will understand why this is important to see the magnitude of the coefficient, number of coefficient, how it is going to relate to the overfitting and underfitting. So I'm going to stop that discussion here and ahead. So here, I was discussing about the linear regression model where you need to draw a straight line or the plane. Sometimes your data set is not in such a way that you cannot draw a line to best represent your data set. So you need to draw a curve. So the drawing a curve is also part of the linear regression, but we call it polynomial linear regression. Means whatever the data point or the output variable, actually what is the diagram? Let me explain. Here x-axis, or suppose y-axis is the output variable, and x-axis is the set of input variable. You consider x1, x2, x3, maybe a multidimensional way. So if the relationship between the set of input variable and the output variable is a straight, or they are linearly correlated, if I say the better way, if the input variables and output variable are linearly correlated, you can draw a line. But if it is not true and the output variable like a y-axis and x-axis points are not linearly correlated, means drawing a line doesn't make any sense. So you need to draw a curve to follow the distribution of the data. So this diagram, through the diagram, I want to clear is that ultimate in the linear regression, what I'm doing just try to follow, try to capture the distribution of the data. So the machine learning most important part in what kind of algorithms you are just studying, follow data distribution is only the learning. If you say what is learning, everybody talk about the learning. If your algorithms can follow the data distribution, how the data are distributed. Data distribution directly meaning of what? the relation between output variable and input variable. If you are really successfully able to capture the relations between input and output variable, means ultimately you have learned the mapping function. So if I feed the input data in a function, the mapping f is a mapping function. A mapping function means like you have learned the data distribution, then you can directly give the output. So these things are really correlated. Ultimate learning is nothing but to understanding the follow-up data distribution. Data distribution means ultimate the relationship between input and output variable, and that called mapping. And mapping is actually a learning. And learning comes in the form of theta 1, theta 0, theta 1, and theta 2, dot, 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 theta n. Mathematically, learning means estimation of parameter. Estimation of, sorry for writing. So, learning means estimation of the parameter. So, because when I was started learning the machine learning, I think many months, many years, I was confused what is learning actually. Actually, in very minute way, in very critical way, what is exactly learning. So it took a lot of time for me to understand, and this is my understanding. It is actually the learning. Mathematically, if the parameters are there in the equations, you need to estimate the parameter. Why the parameter? Because it through that you create the mapping function. What is the mapping function? Actually, it learn how the input data output data is related. That is not actually the data distribution. So here you can understand that if the data are not linearly distributed or not related, you can't or you should not draw a linear line. You should draw a curve, and the curve may be like that. So in typical equations, theoretically, I'm saying if data is like that, it may be possible. It may be possible. Data is like that, suppose. So ultimate, you need to this curve. So in one line, if I say the linear regression is a curve fitting, 100% correct. Linear regression means curve fitting. In the machine learning, it has become a very a booming word like a linear regression. Ultimate, it is a curve fitting. If you know how to fit the curve on the data, means ultimate you are doing the linear regression. So that is a fundamental I have discussed. Let it go. So now over is there. It's we have understood that we need to estimate the coefficient values or parameter values. Then how? Ultimately, we have to go for the learning. So learning is a kind of methodology, a kind of the algorithms you need to follow, or you keep in mind any of the machine learning may have a multiple way for training. So don't think 2 plus 2 always 4 here. If you change the learning and training method, you will get the different answer, different model. So conceptually, I'm talking about if you have a linear regression, simple, whatever the linear regression you have fixed over here, like y is equal to b0 plus v1 x1, it is fixed, but it may have a multiple training method 1, training method 2, training method 3. You apply, you will get the model 1, model 2, and model 3, and believe on me, it is 100% going to be different model. Performance of M1, M2, M3 ideally should be almost similar, but theoretically they are going to have a different model. So because that different method you have used, but means different way of learning you have adopted. Similarly, in the case of linear regression, we have a multiple training method like a least square, one of the most famous training or learning method of the linear regression. Gradient descent also, I think most of you are comfortable and you know. And more like maximum likelihood functions are there. There are many ways. So today, with the limited time, I'm going to discuss about the least square method, how it works. Working of the least square method for the training of linear regression model. So I will explain with it very simple example. So let me open the example. Through that briefly I will discuss. Suppose this data set is given to you. Okay, I think it is visible. And the data set is simple. The size of the house or flat, you can consider it is given on the left hand side, and the price of the each and every house on the right hand side. My objective is to that in the real life, I want to give the input level like the size of the house, and my linear regression model should predict the price of the house. So first, let me discuss about the distribution. So this is the way I have drawn the plot between the area versus the price, and we have seen the data are almost, you can consider, are linearly distributed. If the data is linearly distributed, my objective is to draw a line such that every data point ideally must be on the line, but it is not possible to achieve the ideal case. So the data point must be very close to the line. That will be my objective. So this is the objective I have discussed. So ultimate, what I'm going to do, the price is going to be output variable, theta 0, theta 1, and area. Since it is a simple linear regression, we have only one input variable, area. So area is going to be the input variable. And theta 0 and theta 1 I have to estimate. How? So suppose this data point is given to you. So the question is that we need to draw a line, but how can I draw a line? Suppose you can assume that randomly I have drawn a line that is going through this data point. But many of you may think, why this line you have drawn? We may have a different line. So theoretically, manually, you can draw multiple lines. Suppose this is the way you can draw these. Suppose these are the data points. These. Thousands of lines you can draw. Okay. So theoretically, you can draw. Mathematically, how can you draw the multiple line? The question is that. So in mathematically, you can draw a line by many ways. Either you can change the slope of the line. The moment you will make the change in the slope of the line, you will get a different line. Or you can change the intercept of the line. Then you will get again a new line. And you can play with the both together. So now you can understand what is the use of the parameter slope and the intercept. It is used for drawing the different line. Rituraji, hello. Hello. Kuldeep sir, are you there? Let me work on that. Rituraji, I am audible. Hello. Hello.
Yes, sir, you are audible. You are audible.
No. Rituraji. Sorry, please expel him. Please expel him. Block him otherwise.
Yes, sir.
Actually, he is not interested to join. I think just for a certificate purpose, maybe there. So block him or unregister for next lecture.
Fine.
Hmm.
Fine, sir. Fine. Sorry for the interruption.
Okay. So that was the tool by which you can draw a multiple line mathematically or programmatically during the implementation. So now the next question arises, if you have a multiple line, how can you select which is the best line, which is the final linear regression? Multiple line means ultimate multiple linear regression you have. So if you have multiple lines, multiple linear regression, how you will select which one is the perfect or the best one? So that is the responsibility of the underlying least square training method. How it works? You do one thing like you see. Suppose this is the data point like 1000. Here you try to see what I am pointing over here. 1000 is the area of house, and accordingly, what is the price of that house is like 35 lakh. So these white colored data points are the real data points. You see, area of 1000 square feet size is 35 lakh. So similarly, the area of 1200 square feet of house is like more than 46 lakh, like that. But I have drawn this line So whole data set I'm going to represent by this line, and this line is suppose I will use for the prediction purpose. So I have to check how well the line is predicting. So suppose if this is the line, and if I feed the input, I don't know about the output. If I feed the input, so I have to draw a line. I have to cross that line at the point, and again that point, what it is predicting? It is predicting 25 lakh. So actual value is 35 lakh. My line is predicting 25 lakh. Similarly, for 1200 square feet of the house, my line will predict like 30 lakh, and actual price is like 46 lakh. So what is the difference between what is the actual output and the output given by my line? I will say it is error. It is given by the error. So each and every data points of the line will contribute some error. So I have to gather that error and I have to sum it to find out the overall error given by your line. The best case is that if data points are on the line. If the data points are on the line means actual output or the predicted output is same, the error is 0. That is the best case. So here you can see it is the actual output, and it is a predicted output given by my model, and this is the error. So you might have observed that some of the error are positive and some of the errors are negative. So if you're going to sum it directly, the error, the negative error going to cancel the positive error. Ultimate, the total error, whatever you will get, it will not give you a clear picture of the error given by your model. That is one of the reasons. There are many reasons, and one of the reason is that you just square the error. Square the error means ultimate you are going to make all the error positive, so that it is not going to cancel the error each other. So there are many reasons. One of the reason is that to make the error positive. Otherwise, many of the person, or you may ask, you can take the absolute value. So if you take the absolute value, then it also we can solve this problem of negative and positive error. But there are another advantage if you square it and solve it. I'm not going to touch that advantage. The advantage is a mathematical advantage. If the things are in the square format, ultimate, it comes in the better format mathematically to apply the derivatives. Ultimate in the underline, we are going to apply the derivations or derivatives. So if the things in that format, it makes the things very simple and easy. So that is another reason. I'm not going to touch over there. So in this way, the formula is there. If you have m number of data points, so whatever the data point is there, and against that data point, whatever the y hat means predicted value, we square it, we difference it, square it, and try to sum it. So it is called least square error. That's why it is called least square method. So why the word least is there? Because ultimate, what is my objective? I want to make this error the least. So ultimate, here I'm going to say a lot of models are there. You have, suppose, least square error 1, least square error 2, least square error n. Suppose n number of line you have drawn. So which will give you can say the least value or minimum error given by which line. Suppose this is the line that have a minimum error. So I will consider this line as a final line, and I will discard other lines. So that is the underline method. I have explained how to draw multiple lines. Once you have multiple line, how we will select the best line by applying the least square method. The method is very simple, very much simple. That's why name is given the least square method. And sometime if you have a more number of input variable, like a number of bedroom also there, price of the house also there, like it was there earlier, then you need to draw a plane. Okay, so similar concept is there. So the difference between like here, whatever the value predicted by my models, whatever actual value, you minus it, square it, and sum it, like that. So whether it is a single variable, whether it is a multiple variable, the same concept you can apply. Okay, some point I will okay. Another example I have taken where there is no linear relationship between input variable and output variable, like age and salary of a particular person. Suppose this data set is given to you. You can plot it. By plotting, you can sense it whether you should go for the linear regression or polynomial linear regression will be the better solution. So here you can see the relationship between age and salary as per the data given to me is not linear. It is a little bit curved. So by sense such kind of relationship, you may decide the linear regression is not a good solution and go for the polynomial linear regression, like that. So what is the polynomial linear regression? You know, it is a simple linear regression. The moment you increase the degree of polynomiality, means you say here I will include the theta 0 plus theta 1 age plus age square also you may include. Okay, so age to the power 3 you can include. So the moment you started including the parameter that have the degree of polynomiality is more than 1, ultimately you are developing the polynomial linear regression like this, age and age square. Now it's up to you. You can include both the parameter age and age square together or either one. So it is not a rule means the age square, if you are including, you need to include the age also. It's freedom to you. It is a hit and try, and which combination of the input variable will give you the better performance you have to select. So there is no any clear guideline, there is no any clear rules whether you should include the x if you are going to include the x square. So the freedom is up to you. It is a hit and try. So similarly, keep on increasing the degree of polynomiality like that. So it is the way you can choose for implementing the polynomial linear regression model. So I'm going to close it and going back our discussion. Here the least square method I have discussed. Now the sum of the prerequisite I will discuss. I will not going to cover all the prerequisite. And suppose the data set is given to me like insurance data, and I have decided to apply the linear regression model for solving the problem. Then I have to see whether my decision is correct or not, or I'm wrong. So the linear regression model or machine learning algorithm, the first prerequisite is that linearity. The relationship between two variables must be linear. So what is the relationship? You see, the expenses is the output variable. Ideally, please note my word, ideally, the relationship between age and the expenses independently, different, separately I'm talking about. And it is a categorical variable, I can't compare. It is BMI versus expenses. Suppose two numerical variables are there. So the relationship between age and expenses or BMI versus expenses ideally must be linear. Or anyhow, if you can combine the impact of all the input variable, that combined impact must be linearly correlated with the output variable. That is a one assumption. The error of the prediction are distributed normally. So like it is talking about during the training, you suppose you have m data points. So you will have a m number of error 1, error 2, error 3, like m number of error. If you create a histogram or data distribution, ideally it should have a norm. It should draw a normal curve or normally distributed. It should have a Gaussian curve. Again, a lot of time or discussion may be there, so why it is. So we don't have much time. Okay, one session we have. So essential part I will cover. And the important part is that whatever the error given by your model, whatever the model you have selected, if you draw that error should have a Gaussian curve. It is written. Okay. So I'm not going to touch that part. The important part I am covering. Another important discussion and assumption is there. Whatever the input variable, I'm not touching the output variable. Whatever the input variable you have, if you try to find out the relationship between the input variable like age and gender, age and BMI, age and children. So basically you will try to calculate the relationship between the input variable. It must be independent. Please try to focus on my word. These internal variable must not correlated each other at all. It is an ideal condition. So they should not have any relationship between or among the input variable. So how do you ensure that the input variables are independent to each other? The answer is that one of the solution is that you can calculate the correlation. You can go for the correlation analysis. So if the two variable like age and BMI suppose are correlated, so they may be positive, may be negative. So the value may be like a -1 to 1 like that, where one is a highly correlated, -1 is also highly correlated, but the negative way. So ideally, if I try to calculate the correlation between age, BMI, children like that, so it should be zero. Ideally, ideally should be zero. So like a 0.0. So you see over here. So the correlation value for age and children is 0.04. It's good. So here it is a little bit big, or it is also close to 0.1 like that. So ultimate critically I must say, if any of the value, if you encounter is very big value like 1 or -1 close to 1, so you should give your proper attention. Means these two features are internally correlated, you must solve it, then go for the training. How to solve it, again our big chapter. Okay, I'm not going to cover right now. And one of the most and another parameter is that homoscedasticity. So what homoscedasticity says that, suppose this is x-axis is the input variable and y is the output variable. Okay, so you see the distribution of the data along with the line. So suppose this red color is the linear regression line you have come up with the after training. So this is the line you have finalized. So you need to see it, the homoscedasticity. Homoscedasticity says that whatever the data points are there, the distribution of the data points should be same from beginning to end of the line. So the example I have pasted over there, it is violating the homoscedasticity. It is the example of heteroscedasticity. Why? You see the second half first. Most of the data points or almost all the data points are densely and very closely distributed around along the line. But first half you can see the data points are not equally distributed along the line. So throughout the line, the data distribution ideally must be same or equal. So it is called homoscedasticity. Many others dependencies are there, like another example, if the data point is like that, it is a heteroscedasticity. It is also heteroscedasticity. It is example of homoscedasticity. So these things you have to recheck every time once you're going to finalize your model. Before modeling, you can't, if possible, once create the model and then see how the data points are distributed along the line. And here I'm going to skip it some more technical part. Okay, I will try to include it. So by coding or mathematically, if somebody will say, sir, we have covered a lot of the prerequisite of the linear regression model we have seen, but how can I ensure that? How could I know whether it is following or satisfying the prerequisite or not? So answer is there here. How to find out the relationship, or whether your model is suffering from the homoscedasticity or heteroscedasticity, or how can you test it things are linearly correlated or not? So the answer is that once you have trained the model, you have a predicted value, you have actual value that now. This terminology you can understand. The predicted value is given by your model and actual value is already there. You need to draw a curve. If data points are following the line, suppose this is also a line. So here I have not drawn the line. Suppose it is also drawing the line. So if the data points are following the line in unidirectional way, means this the condition is fulfilled and the condition of linearity you have satisfied. Another way is that you can draw a predicted value in the x-axis and y-axis is the residuals. You see if you can see that word. Again, a new terminology I am introducing, residuals. Residuals means errors. So you know the errors you have, errors means number of data points you have a number of errors. So you can draw a curve between errors versus predicted value, and the data point ideally should be distributed symmetrically around the plane. So suppose it is a okay. Suppose it is a half of the plane, so the data distribution should be symmetric. The way data is distributed, the first half of the plane, the same area it should cover by in data points in the second half. So it should not create any clusters or any pattern. So you can see it is not a pattern. Data are covering every part of the area. So if it is like that, you are satisfying the prerequisite. Otherwise, you need to relook. A lot of solutions are there. So okay. So the same thing is there. I'm not going to cover it. Suppose here again the fitted value means the predicted value, and this is the errors, I think. So if it is making some curve over here, you see, so a lot of data points are at the initial parts, and the later you go ahead, the things become very sparse. So it is not ideal case for the linear regression. You should stop it, and you need to relook again the problem with the data set you have. You try to solve it through the transformation to the data pre-processing techniques. Moving ahead, many theoretical parts cover, I need to go for the coding. So suppose, how can I do? Yeah, so suppose this is the equation is given to you, where the expense is the output and all are the input variable I have written. So you may have a multiple models. Like initially I have explained, it's up to you what the number of what kind of input variable you want to include in the equation. So someone may come, sir, in the output variable the same for everybody. The input variable, someone will say, I will include all the input variable in my equation. Someone will say, sir, why? I will include in the age only. Someone will say, okay, no, age plus gender I will include. Somebody will say, okay, no, age plus gender plus BMI I will include. All are correct. Theoretically, at the beginning, all are correct. And every model with this equation I have to train on the data set, and I have to see which model give the better performance, which models give you a better satisfaction against the prerequisite. Accordingly, you can decide which is the best one. So actually in the life, in the real life, it happened like that. We can't stick with the one model. Whatever the permutation combination possible with the form of input variable, you should try and come up with the best model. Okay. So here I'm going to write the code for one. Okay. Here. Normally when you install the R package, the LM is the function, that is a predefined function. Whatever the linear regression model I have explained with the least square method is already implemented in that function. You can directly use for your purpose. So it automatically comes with by default in the R environment LM function. If it is not there, you can use additional libraries. A lot of libraries are there. So one of them is the Carnet. So if the LM function doesn't work with your environment, means dependent library is not with you. So you need to install the Carnet package. But ultimately it will work. So LM function I'm calling, and syntax is that I have to write the first output variable, then tilde, then other input variable you can include by using plus sign. And which data set you are trying to work with, that one you have to pass a third parameter, data is equal to insurance, because in one go you might have a multiple data set into the R environment. So you want to train your equation in which data set. So data sets you have to provide, and whatever the model you finally will get, I'm going to give the name LR underscore model. You can give the name according to you, A, B, C, D, X, Y, Z, whatever you want. So just for you, I'm going to copy it. Okay, going to paste and just enter. Your first model you have created. So in the last 3 days, whatever we are learning, only for understanding this line, means model. We are talking about machine learning model. We are talking about training, testing. We are talking about everything happened in this way. Testing it didn't happen, but training is over, and the model name is the LR model. All it has drawn a lot of line. It has calculated the error. It has squared it, and it sum it and finalize the line that gives the least error, and that model is saved under the variable name LR underscore model. The one line, everything is over. Okay, so now I want to see how the model is. Many parameters are there, so I will not cover all the parameters. Some of the parameter I will cover. So model is there. Just print the name, and it says about what was the formula. Formula was the expense was the output variable, and these are the input variable. You have to include, and you have included, and the output, and with the data set inference you have trained over. And you see the intercept B0. B0 is minus 11,941. So there is no importance of minus and plus over here. First try to understand. So there is no meaning of negative and positive value. It is a B0. So age coefficient is 256. Children coefficient is 475. So ultimate, if you say, for a simplicity, where is my pen? Yeah, sorry. So ultimate, suppose expense was the output variable. Suppose this was the equation, age plus B2 children plus dot dot dot. After training, training algorithm have estimated value of B0 was I think 11,971, whatever you want, plus B1 was 256 age, B2 was 475 children, like that. So this is the linear equation line we have received, and through that you can create. Here the answer is given over here. It is a coefficient. This is a coefficient with respect to the children, with respect to the age. It is an intercept. Okay, so that was about the model. Many things are there. I'm not going to touch it. And there is a yeah. So let me explain the interpretation of that output. So it says that what is the meaning of 256? So the coefficient of the age in our model is saying that every 1 year increase in the age of a person, required expense goes up by 256, because machine learning is all about the interpretation. So how can you interpret the model? And so we can say that's why age is nowadays very much important in the form of dollar. If this year you are your expense is 100 rupees, next year it is going to be hiked by 256, because 1 year increase in the age. Your data set says that the person have to increase their expenses by $256. Similarly, children, or you can say the dependent in the family, if you have one more dependent in the family, ultimate, you are going to expend $475 in the next year. So similarly, based on that BMI, like that, you can make the interpretation. Now there is a summary command. It will give you more one level of detail about your model. So if you call the summary command with the model, it will give you a lot of things. So I'm not going to cover each and every part where it is giving like the estimate means like a coefficient. These are the you can see this is the name of the variables, first column. Second is the coefficient of the variable. This is the standard error. Okay, so we need to, if you interested to work on the linear regression, you need to understand t value p-value, many things are there. Okay, so it is not part of today's discussion, but I am saying how the R is comfortable in the one go. You don't need to write the code to calculate the standard error, t value, p value. Many things are preloaded. That is a simple LM function. In the R, more advanced linear regression package libraries are there. They also give a more number of detail or statistical value. It is useful for you. Residuals error, residuals standard error is 6062. So here I am wrong, but you can consider it is a total error. So when we during the least square method, I have explained the total error. Total error what was? The square of all the errors. You have to sum it. Summation of all the square of the error. So for a simplicity, you consider it is a total error given by your model. Degree of freedom I have introduced earlier, and it's your suggestions. I'm giving the session to please go through it if you want to excel your career in the data science. So the total error given by your model, and in the R squared, there is a adjusted R square and R square, both are the different, but for a simplicity you can consider. Other parameter I am not considering. So it is a total error given by your model. It is R squared. R squared is a parameter, like in the classification, accuracy is the parameter. So definitely R square is a parameter. Ideally, the R square vary from 0 to 1. The R square is a performance measure. I'm not going to discuss its derivation. So it is 0 to 1 value. Okay. R square vary from 0 to 1. And I always prefer bigger value. Always prefer bigger value. Means R square of model with R square with bigger value will be better situation. Okay. So here the two parameter I'm just discussing. Another parameter I'm not discussing over here. First one is the standard error. Residual standard error means total error of your model. That was this one. R squared, it vary from 0 to 1, and in this case the R square is 0.75. Okay. Now I need to check the error, like I have explained the error given by your model. I have explained somewhere. It should have a Gaussian curve. It should have a Gaussian curve. You can see I have seen, I have discussed. So how do I do? So residuals is a function. Residuals means error. You need to pass your model in the residuals, and that function will calculate the error given by each and every data points, and is going to store in a vector. And the vector is a data type or data structure. I automatically would create a name of that vector is the error I am going to give. Whatever the name you prefer, you can give. So the code I am going to write, the total error. Now the total error is here. You see, this is a vector. Size of vector is equal to the number of data points. So here the first one is that this is error given by the first data points. Means whatever the data points, the actual value is 16,884, and my data points are given. The error is minus this one, means depend on where you have put the term actual and predicted, and the difference is this one. Similarly, the error given by the second point, third point, like that. So you can draw a curve. So for R, you need to call a histogram. HIST is a function. You need to pass the vector, and it will create a histogram for you. You see, it is not in the ideal format. The bar should be like that. It resembles with the Gaussian curve. Okay, it is not ideal case, you can see. So that is the way you should follow. I'm just going to demonstrate. Okay. Now we need to draw a curve between the fitted value like that. Residuals means error versus predicted value. So you need to call a function like that, where model whatever you are using, dollar fitted value means actual value, and errors whatever the model you have used, percentage residuals. So it is going to draw a curve like error versus, here I think this is a curve. Fitted value means actual value versus model, like that. So you can see, if you remember, it should be equally or symmetrically, the data point must be appear on the plot. But here you might have observed it is closing a very dense cluster here and there, means this is the prerequisite is not fulfilled by my model. I should not go ahead. I need to relook in the data set, play with the data set, apply a lot of transformation techniques, and again train and test, train and test, and train and test, like that. So many things you can do, many things I'm not covering here. So here the optimization is a last part I kept for a discussion, how to optimize it. So my meaning is here, suppose whatever the model is there, the total error was like 6,000 and something. I want to reduce that error. R square was 0.756, like that. How can I increase the R square? So you can think the data set is given to you. I have sensed it. It is not good to apply the linear regression. I should apply the polynomial linear regression. For that purpose, first attempt I have try to see the terminology. There is no rule what you should do ahead. You just try it. So what I have done, the age, what was the age? I'm going to square it. So this is the code I'm going to write to squaring the age. You see, so how to access the particular age column? Yesterday we have seen the data set variable name, then percentage, dollar, then the name of column, and this is the code for squaring it. So once you square it, you can replace with the new variable I'm calling age2. So you have done, I have created. So now you can access it. It is age square. Whatever the age was there, it is square, it is square, it is square it. Now this new parameter I'm going to include in the equation. We see age2, the variable name is given the age2. So I'm going to use the age2, children already there, BMI already there, gender already there, smoker already there. You might have noticed that here I have removed the age, but it's up to you. You can also include the age over here. So just suppose this setting I'm going to copy and paste over there. The model is already within a second is trained, and name of the model I have given the LR model 1. So now you see the summary to see whether the total error of the model we have improved or the R square we have improved or not. So you see there is no much big improvement. It was earlier 6062. I have written over there also. Yeah, earlier it was 6062, and I reduced in very minutely, a very less improvement is there. Now it is 6029, and I think there is no improvement with the R square. So earlier I have seen you can play with that. You can include both the variable like age plus age square. Okay, so let's see, and the name of the new model I'm going to give you LR2, and it is trained, and summary of LR2, let me call that function. You see the 606, even it increased. Earlier the error was 6029. The moment you included the new model or both the parameter, error increase. It may happen sometime. There is no there is a small improvement in the R square, like it was 0.7536, now 0.7537. like that. The last point I'm going to discuss, this is called adding the interaction effect in the modeling process. So the background I will not discuss, we don't have much time here. But the concept behind is that in the input variable, there may have a situation like, suppose any of the 2 or 3 variable, like for example, BMI in children, they are independent to each other, or they are important variable and they are going to impact the value of expense. I agree with that one. But the combined effect may be such that the combined effect, if I am able to really include in my model, I don't know how, the combined impact I'm going to measure or going to see the impact of your model, it will give you a better way to improve the performance and accuracy. So if 2 models are totally independent but may have a combined impact, for example, suppose BMIs talk about the overweight or underweight, or the smoker talk about whether the person is a smoker or not. Both are important. If there is no relationship, if the person is overweight, the person will go for the smoking. A person with underweight will not go for the smoking. So in that way, you can conclude the BMI and the smoker, 2 variables are not correlated. So if you increase the value of one variable, it is not going to impact the value of another variable. That way you can check the variables are related or not. So if the 2 variables are independent, but you can say how, when you combined these 2 variables, how it is going to impact the expenses. You try to see. Suppose there is a 2 person. The person is perfect in their health, weight, the BMI is very good. It's a good person. One person is very overweight. If both the persons are smokers, so smoking is something, it's a bad habit you can consider. It is going to impact the body of the person more severely if the person is overweight. So so many discussion may be going on, but in majorly, it have seen by the research, if the person is heavyweight or overweight, the impact of smoking is more severe in the coming future. If the person is the smoking is not good, everyone, or it's bad habit, but if the person is in balanced weight or good, it may harm the body of that person is smoking, but not as much as severely than it could possible with the overweight. So this is the theory and concept behind how the 2 variables are independent, but if you combine the behavior, it becomes very important to consider in the modeling. So theoretically it is over. Conceptually, how can I consider? The answer is that you need to include the product of that variable. So like a BMI and the smoker. So it's a new variable I have created, like age square, children, BMI independently, gender, BMI and smoker, the new variable I have created. Because I have a domain knowledge, these 2 variables combined impact is meaningful. So once you have done the same things and created a new model name is model 5, suppose. Let's see whether it is working or not. So like I have created the model and the model name is LR5. Let me call the summary command for that purpose. You see, the answer is here. I have pasted the answer like, you see, earlier error was something 60, means around 6,000. You can see the error 6,030, and the R square was 0.75. The moment you have included only one more term, you see the magic. R square increased by around 10%, more than 15%, it 0.75 to 0.86, and the error has reduced drastically from 6,000 to 4,400. So that is the magic of understanding. If you have a domain knowledge of the application you are working, you can do wonders. because nobody is here going to do which input terms you need to combine. There is no formula, there is no answer. Ultimate background knowledge you must require. Okay, so in that way it comes under the optimization. Once means once the preliminary model you have, and you want to improve the performance of your model. So there is many ways or many dimensions you can apply, like you can go with the pre-processing techniques, you can go with the feature engineering, you can go with the including with the interaction term, you can go with the increase the degree of polynomiality, like many ways you can apply, hit and try, and see the things are working for you or not. So with this word, I'm going to end my session, and the summary of session is that really any kind of machine learning algorithm prerequisite become important to consider, to learn, to check, to evaluate. And without having knowledge of prerequisite of the any of the algorithms, how the algorithm works, that knowledge is not enough. Model optimization, under that, sky is the limit. Variety of things you need to explore, you need to understand, you need to implement, you need to hit and try almost. Various parameters are there that is not a part of, that was not part of today discussion, like that adjusted R square, standard error, p-value, chi-square, and many kind of mathematical functions are there that people are using for evaluating the performance of the linear regression model. So that are the things that are I couldn't cover for a today lecture, but I think it is, I hope it is enough to frame a background and enough terminology I have covered during the lecture that is make you more motivate and help you to understand the books and blogs and other material when you will refer for understanding the linear regression model in a better way. So in these words, I'm going to end my lecture and open the discussion forum. If anyone have any issue or any questions, please write on the chat box or directly unmute and ask to me.
Thank you. I mean, yeah, now the floor is open for question and answer. So we can
So what is the
ask
significance
to
of
we can
adjusted R? Hello,
So
sir.
the many questions just I'm observing it is we didn't I couldn't discuss during the lecture based on that you are asking the question. So it is not possible for me the answer because I have to go with the whole discussion about the adjusted R square.
Okay,
And
so one
what
question,
I will
sir.
summarize, wait, I will summarize. Adjusted R square is the regularization techniques. So regularization means what? Whatever the measure you are using, like a R square. R square have some problems. So the moment you will increase the degree of polynomiality or increase the number of input variable, R square will always increase. So you will be misguided. My R square is increasing means whatever the things I'm playing with my model, I'm going into the correct direction. But it always sometimes misguide. So we need to give the penalty on the R square formula, R square derivation. That penalty we call regularization. Regularization, the concept of machine learning, not is the concept of the only the linear regression. So that's kind of penalty, kind of regularization. And better always use the adjusted R square in the life. Do not use the R square. So I think more than that I cannot explain right now.
Thank you, sir.
Good afternoon, sir.
Good afternoon. Good afternoon. Yes, please.
Yes, sir. Sir, I was having a doubt. If we assess the model through R square or adjusted R square value, but when we get the higher R square or adjusted R square value, say upon point 0.9 or 1, we tend to say that the model is overfitting. So what is better? Like we should check for overfitting, or we should go for higher R square?
Overfitting is the things that you never or you must not avoid. So overfitting means what? The performance you are observing in the training data set, it was very good. But once the same model you are going to test with the test data set, the performance degraded a lot. Means what was the performance we have received in the training data set, the same performance were not given by the test data set. So why is the big difference? Because your model have overtrained with the training data, it has memorized everything from the training data, but the moment you will going to check with the unseen data, that is called test data, it fail. So you don't need that model that have R square, very big R square in the training data, but in the real life it fail. So R square is something that will help you to find out whether your model is overfitting or underfitting. How? If in the both case, the R square for the training, R square for the training is same in the both case or almost same, then your model is very good model. It is not underfitting, it is not overfitting. So the R square is the something, any kind of parameter in the world, maybe accuracy, maybe anything. You need to think in the holistic way. The performance measure given by your model should be almost similar in the training and testing phase. So it is not true if the R square is very much big R square in the training during the training and testing it fail, you should continue with that model. You never continue. I hope it is clear to you.
Yes, yes. Thank you, sir.
Thank you.
Hello, sir.
Yes, please.
Sir, please, if possible, sir, please define the difference between the R square and adjusted R square.
Hello.
R square, and what is the difference between the R square and adjusted R square?
I have already explained. We don't have time to explain the mathematically. I have already explained the R square have a problem. It always go hike and always go increase the moment you increase the number of parameters, number of variables, degree of polynomiality. So if you depend on the R square, the moment you will increase the degree of polynomiality or degree or input variable, if R square increase, you will think whatever you are doing, it is a correct. You are going in the correct direction, but ultimately it is not good. So the formula of the R square, they have changed and they have given the penalty of that formula, and the formula increase in the case whatever the experiment you have done with the variables with the degree of polynomiality, if that experiment is really impact the performance of your model is a lot, then the R square, adjusted R square increase. Otherwise, adjusted R square also may decrease. So the regularization form of the R square is adjusted R square.
Thank you.
Intentionally, I'm not going with the formula because it will take again 15 to 20 minutes to discuss over there.
Hello.
Yes, please.
Sir, please explain the significance of p-value in very brief.
It is not clear to me. Please repeat it. It is not clear to me.
Sir, please repeat explain the significance of p-value in determining the what we can say that power of model.
Yeah, same questions in during the lecture I have says we cannot cover all the aspect of the algorithms in one lecture. So the p-value is something that talk about the significance of the variables, significance of the model also. So if the variable is really contributing, so suppose for example, briefly conceptually I'll explain. Suppose you want to calculate the salary of a particular person. And the variables are age. You can say, yeah, age is important. Education is also important. Kind of city like metro where it is living is also important. If uh, hair color of that person, okay, it is going to decide the salary of pen number of that person. It is going to decide. car number of that person is going to say salary. So how could you know?
No.
Suppose I'm saying I'm not giving these name, I'm giving x1, x2, x3, x4, x5 and 6. It is not given to the data set. I have encoded all those values like x1, x2, dot dot x6. Then how can you say which variable is important or not? This is the question. How do you know? Answer is the p value. One of the answers is the p value. Yeah. So if the p value is significant, means it is less than 5%, less than 5%, or 0.05 sometime. If any of the variable, typically we'll say such variables are important. So here it is already there. It is already there like that, like that. This is the p value. So 3 star means the variable is most important. 1 star means the variable is okay, 0.05, and this variable is not important. You see. So purposefully with the limited time, I didn't cover that part. But hope the basic concept of the p value I have explained. Mathematically, we need to learn. How it is happening.
Okay, sir. Thank you. Sir, it is always necessary to have value less than 0.05, or we can take 0.1 also.
It statistically it is fixed 0.05 is the comes from the literature. They have like value fixed. If value is less than this, the variable is important. Otherwise, variable is not important. Ultimate, the p value is also used for the hypothesis testing, like a null hypothesis. So like a new word I'm covering the hypothesis. Please study what is a null hypothesis. So every time you have to discard the null hypothesis. So there also use the we also use for the p value in that part.
So we can say that p value is a degree of freedom.
No, p value is not related with the degree of freedom at all. Degree of freedom means number of variables you are using with respect to the number of data points you have. You might have observed over there the degree of freedom is okay, starting with that one.
So
The
that
degree
means
of freedom is 1329. The moment I have included the one more variable, the degree of freedom it decreased 1328.
So sir, exactly we can say that if our p value is less than 0.05, we are accepting null hypothesis. And it is a symbol of good model.
You have to write. No. You have to explain the null hypothesis. Null hypothesis means what? Null hypothesis you have to write and yeah.
It means that assuming our assumption is true, whatever we have whatever we have thought is
null hypothesis. Yeah, null hypothesis is the opposite whatever you are thinking. Like you are saying you're talking about with respect to the age. So null hypothesis says that age is not important parameter, not contributing to decide the value of salary. That is null hypothesis. So opposite is that if the age p value is less than 5%, means the age is going to impact the value of salary. So we can reject the null hypothesis. Similarly, null hypothesis not only we can use with respect to the individual parameter, we can use with the combined parameter that model wise p value you can also use. Like you can see here the p value. Look here.
This
is also p value, and this is also a p value, complete model wise. Yeah, please.
My last question, sir. The p value here in model, can we correlate them with the null hypothesis in this particular?
Your voice is not clear.
Sir, can we correlate?
You are Rituraj?
Yes, sir. Sir, can we correlate this null hypothesis concept here in this modeling also, in this particular modeling, or not? They are distinct apart.
Yes, you can relate. Wherever you are using the variables, you can relate it.
Thank you, sir. Thank you for it.
Thank you. Other questions, please? Because I have introduced a lot of terminologies, that's why a lot of confusion is there, a lot of questions are there. It is very good. So ultimate, if you have a lot of knowledge, a lot of terminologies, you may have a lot of questions, means you will go for finding those solutions, maybe with me, maybe from the Google, maybe from other platform. So that is the objective of the lecture, so that you may have such terminologies in mind and you can go for the learning. Any other questions, please?
Sir, I'm sorry to interrupt once again, sir. So the thing is, I read somewhere that if the number of data point is n, so degree of freedom should be n-1. Is that correct, sir?
1 means what? Why 1?
I don't know, sir. I always saw in some papers it is 1 minus 1.
You are correct. Actually, the generalized formula is that if there is a n number of n is the variables. Variables means features. Okay, maybe 1, 2, 3, 4, 5. M is the data points. M is the data points. Okay. The degree of freedom is always be m minus n. Okay. And 1 minus extra 1, why? This is for bias, for intercept. You recall.
Okay.
But if you are not using any one of the variables, means you are using only bias, only intercept. You try to remember.
Okay.
Means equation is like b0 plus b1 x1 plus b2 x2. Like we don't have input parameters. We have only b0. So that's why 1 always be there. Now you got it, I think.
Yes, sir. Yeah. Thank you, sir.
Thank you. Thank you.
I think, sir, this will go on. Yeah, please.
Sir, if I am correct, that the degree of freedom is number of independent variables which you can freely
I think background, sir, sorry. I think in the background something is running or your speaker is on. I think so. The dual voice is coming to me.
Great. Now it's yeah.
Please.
Okay. Apart from Rituraj, sir, anyone else? Any questions?
Actually, I want to know about auto regression, maybe a little bit.
Auto regression is which context? I'm not able to understand. Auto regression is not an algorithm. Maybe it is some kind of customized version that a lot of please.
In medical terminology, how to use it?
I don't have that answer actually. I don't know that part.
Okay, so you have explained the linear equations or linear regression. So there are some multi-valued and multi-variable. What exactly that is? If you can throw some picture of it in a precise way.
So if you have a multiple variables and then it is called multiple linear regression. So every books and blogs or literature are using the same concept and then going to represent by using different terminology. So don't confuse with that one. Whole concept is similar. Multiple linear regression, sometimes called multivariate, like that kind of things. So conceptually both are same.
Okay.
Okay, Kuldeep sir, I think, please.
Yeah. No questions now. So, thank you once again, sir. And I thank all the participants, first of all, for being so interactive and so listening so passionately. And I strongly believe that you must have learned a lot of things, a lot of basic things, a lot of advanced things in this machine learning techniques. As Tiwari sir has already mentioned, that if you need any kind of help, we are always here. You can write mail, you can contact in any way. So now, thank you again, sir. And if someone will be having any doubt, he will contact you in the participant side.
Always, sir. Always.
Yeah. Sir, can we have the CSV file log on data set?
Who is this?
Yes,
Mr. Rituraj, please mute yourself. Your voice is not clear. Yeah, thank you.
Rituraj, your voice is really not clear. A lot of disturbance is there. So.
Okay, no issue. So thank you, sir. Thank you again. We are winding up this session here.
Thank you, sir. Thank you.
The speaker, and we will be again joining Vana Kumar, we had very good session. Thank you for your comment. We'll be having the next session on portfolio risk management and everything by Professor Siddharth Chakravarti at 3 p.m. So I request all of you to please join the session at 3 p.m. and this session is winded up now. Thank you, everyone.
Thank you, sir. Thank you.